I know my lighting situation is terrible, and also my hair is drying, so that's why it looks weird. But I'm gonna talk about the resistivity lab and kind of talk about like what it means in the greater scheme of circuits. So um, resistance, right? You look at the resistance of a resistor or something like a wire, right? A lot of things are really resistors, right? Resistors just stop or like prevent the flow of electrical charge or electrical current, right? And that boils down to like conductors and insulators. Conductors allow for the flow of electrons. They allow for current, right? They don't resist it as much as like a blanket or something with wool or like something organic that is an insulator. So the resistance of something, right? The resistance of a resistor or even like a copper wire, right? Wires still have some resistance. So the resistance of something is determined by three things. Rho, which is the resistivity of that object, the length, and then the length of the resistor. I'm going a little bit too fast. The length of the resistor, right? So if you have a wire, I don't know why I'm explaining length. It's how long the wire is or something like that. And then the area. So the area, right, if I had my circuit going through this resistor right here, I have a length L. The area would be kind of the cross-sectional area. The area, like, this is our current, right? Current I. It's like the area that the current crosses through. So, bigger area means less resistance, right? Think of it as like water, right? If you have a bigger pipe, water can easily flow, and Bernoulli's principle and all that stuff. So, they this is kind of like resistance for wires and things like that. Like a light bulb doesn't really have a length or an area or a resistivity. It's made up of a whole bunch of things. But when we're looking at copper and gold and silver, all sorts of materials that you can make wires out of or whatever, you can figure out the resistance using this equation. So just some couple things to note. So if this is the resistivity is resistance is proportional to rho. If your material like gold has twice the resistivity for a certain amount of length and area, right? Like if these two are constant and then I double the resistivity, you get double the resistance. Gold is just more resistive compared to copper. That's probably true. That's probably why they use. Actually, I don't know, but because copper is cheaper, so that might be a reason why they use copper wires. I don't know. I'm pretty sure gold is more resistant than copper. It's proportional to length. If I twice the length of my my copper wire, hey, it's going to have twice the resistance, right? And finally, it is proportional. Resistance is proportional to the inverse of area. If I double my area, I'm going to half my resistance, right? It's double the area. Now, remember, this is area. If I double the radius of this guy, the area changes. So if I double the radius, my area changes by a factor of 4. Why? Because area is the same thing as pi r squared. Now, obviously, this isn't like the general equation. This is like the resistance of a cylinder or something, right? But in this case, for a cylinder, the area is pi r squared. So now the resistance is proportional to 1 over r squared. I'm gonna change my mind. This is just gonna be a resistivity basics video. I'm not gonna go over the lab. This is just how resistivity works. I'm not gonna go over the lab. I'm yapping way too much. But this is the basics, and I hope. Let me just check. How's the light on this thing? I think you could probably see that. I know it's not the best because it's night, and I don't like recording at night. But yeah, resistivity, right? So just some more analogies you want to think of, if you want to think about when trying to make resistance make sense. I always like to think if I'm an electron, right, and I'm running through a jungle or something, like a jungle versus like I don't know, grassy plains. It is much harder to go through a jungle, right? What it's made of. There's a bunch of trees and all this stuff. That's like the resistivity, right? It's the jungle is a lot more resistive to running. Planes, it's just easy. You just run, right? You just frolic in whatever you want to do. You can just run. That's like what the resistance is. The length is like how long I'm going to be running for. So if I'm running through a jungle, if I make that jungle twice as big, you're going to have to be running twice as long. There's going to be even more jungle to kind of get through. It's going to be harder to run through that thing. Area is a little bit harder with this whole analogy. One way I like to think about it is like, hey, if I have a jungle and I make it bigger, everything kind of gets spaced out, right? So the trees and all that's a bit more spaced out. It's actually a little bit easier for me to run, which makes sense because area is in the denominator, right? So that's just kind of some things to think about. And yeah, that the area one is a little bit bad because it's like, you know, this is our jungle. Oh no, this marker's dying. If this is our jungle, right, or whatever, and then I make the cross-sectional, right, so if I imagine this is like my POV, if I make the cross-sectional bigger, you know, it's going to be a little bit easier to run through. I like the pipe analogy better. But yeah, this is kind of how resistance works, and I'll go over the lab now. Thank you for watching.